Hello YouTube, welcome to Logic 103. It's a bit later tonight, but I felt like recording. Last time we left off with these 6 categories, or 7 if you consider these two to be different. We had terms, and these were split in variables and constants, but I haven't talked about that a lot. Functions, which were kind of useless because they can be interpreted as terms secretly. If you remember, if we look at x squared as a function, which is also this graph, then you can view that graph as being a term, because terms can also be collections of points on the 2D plane. We had relations which give truth values, so if you have two terms and a relation, like x is 2, then this equal sign is the relation, and it's either true or false, depending on what x is in this case. Then you had logical connectives, and these first three are dependent on the theory of mathematics that you are working with, but these last two actually live without the theory. So these two are called the basics for first order logic. We saw a few logical connectives. There's the not, or the negation, or and, which are these triangle shapes. We saw the implication arrow, if and only if. Sometimes this one is not taken to be an axiom, but it is a definition, because you can define the if and only if. So if you have A if and only if B, that's the same as saying A implies B and B implies A. But it really doesn't matter if you consider it as an axiom or a definition, in my opinion, as long as you know what it does. And then I also grouped in the false symbol in here, and the true symbol is never used, so don't worry about that one. Some people categorize this as a separate symbol. There's only two quantors. There's the for all and the exists. And today I'm going to explain what quantors do and what theories are. And I'm also going to give the example of Zermelo Freankel choice, which I have been talking so much about. Let's get into quantors. I already gave some examples. This was the first example I gave. All x in R, it holds that x squared is larger equal 0, which indicates that the square is always positive, because if you square a negative number, you get a positive number out of it. And this is actually not logically how you would write this down when you're defining quantors. When you start defining quantors, usually you write it like this: all x, and then x in R, and x squared larger equal 0. But because mathematicians are so used to set theory, and we use this so many times that we want just to look at all the objects in one set, it has become shorthand that if you put the something in some set in the subscript, then you mean to only look at objects in this set, which is what this and statement and this thing here is doing. So let's quickly analyze this phrase here. So these two underlined things are actually a term and a set, which is also a term, and a relation in between them. And this is the same: a constant term, a variable term with a function, and a relation. So these two are both truth values. So if you remember, last time we did proposition logic, and we had things like A and B, which were phrases that could be true or false. But now we supplemented these for actual mathematical phrases. And then the and is, of course, a logical connective, which connects these two phrases. So I hope you understand now how these A's and these B's from last time are actually used in practice, if that was not clear already. So what is this all doing here? It just means that it has to hold for any term in the theory. So there can be more than infinite terms in a theory. Every theory has more than infinite terms. And really the way you should interpret this all is that you're doing infinitely many AND statements. So you look at your first term, let's call it C1, and you're asking, is C1 in R? And is C1 squared larger equal 0? And then you take this statement and you AND it with the next C2 in R and C2 squared larger equal 0. And you do that for every Ci, which is a term in your theory. That's sort of what this all statement does. This first statement here is filtering only for terms that are actually real numbers, which are the terms that we do algebra on usually. This statement obviously wouldn't be correct if we did it over complex numbers. So not for all C in C squared larger equal 0, because I squared is of course -1, so this doesn't hold in the complex numbers. So the only thing you have to do to disprove a for all statement is to find a single counterexample. I give the counterexample of I, and I show that this thing doesn't hold. So let's look at there exists. This one has the same rule where we can use a subscript to when we're talking about numbers, for instance. Let's say there exists an x in R for which x squared is 2. Now this statement of course is true, and for the there is statement you only have to show one example, namely the square root of 2 is an element of R. So the square root of 2 is an element of R, and the square root of 2 squared is of course 2. So here we've given our example, and our there exists statement is true. And there is also, so earlier I said the all statement you can see as an infinite series of AND statements. The there exists statement you can see as an infinite phrase of OR statements. So either C1 squared is 2, or C2 squared is 2, or, and you go on with every C. Now, last time I showed De Morgan's law, or one of De Morgan's laws, which is not A or B, if and only if not A and not B. And this is actually generalizable with, you can add or C, and then here you add this one in the brackets, and then you can add the extra C there. And this one actually also works in the infinite case, namely with the Quantors. So if you have not for all, not there is, and then x, phi x, where phi x is some string that takes in x and returns a true value. So this could be x squared is 2. This thing is the same as all x there is not phi x, which makes sense if you think about it. So you can kind of flip the negation symbol over here. Another little useful tautology, not A is the exact same as A. This follows from the law of excluded middle. So we can add in not everywhere. It's like multiplying -1 by -1. So if we have a for all x, phi of x, then we can add a not in here, and we can take this not and flip it to the other side, make this a there exists statement. So not there exists not phi of x. And then we can remove these two here again. So for all x, phi of x is the same as not there is x not phi of x. And this is sort of the Morgan's law applied to quantors. Okay, so I've shown some example of quantors now. They are like logical connectives, but for infinite amounts of terms, basically. That's the way you can think about them. In practice, they root out all the elements in a set and either say something about them generally or about one of the elements in the set. And that actually brings me to a small tangent. There is one sort of altered quantor that you very rarely see, and that is the exclusive OR version, which we write as there exists with an exclamation mark. So, for instance, this statement would not be true because this quantor is asking for a unique solution, and there's of course two solutions to this relation here. So this would only be true if we only take the positive reals, otherwise minus the square root of 2 would also be a solution. So that is what this exclamation mark does if you see it with the existence quantor. It makes it the exclusive OR statements instead of normal OR statements. Now we've gone over all the types of symbols that you find in mathematics, and we can go on to how to actually describe mathematics using logic. And for that I want to bring up something that I talked about last time. If you have a theory, which is like a collection of sentences, then you can, if you can create a proof tree to some statement A, then we write this as the theory proves A. For example, I gave the example, if your theory is B and the statement B implies A, then this obviously proves A by the modus ponens, the rule for arrow elimination. So what is mathematics in the eyes of a logician? Well, you need a theory, and this theory has a few sentences, and they should be able to prove all the things that we know are true in mathematics. And this theory exists. It's called ZFC, Zermelo Freankel choice, and it has, I want to say, 10 rules, and let's just look at them now that we've seen all the symbols. So this is the first rule. These rules are called axioms. The axiom of extensionality, it says that, well, you can see what it says here. For all x, for all y, for all z, it must hold that x and z, then if and only if x and y implies x equals y. And what this statement does is it imparts the equal sign with the meaning of this relation. And at this point it's handy if you know what this relation means. So if I write down the number 2 and a set with 1, 2 and 3 in it, then this is true. But if I write down 4 in the set with 1, 2 and 3, this is obviously not true because 4 is not a member of this set. So we have to cross it out or do a not thing in here. I can also name sets, so I can say, if I want to write this shorter, I can say 1, 2, 3 is the set A, and then I can write 2 in A and 4 not in A. Now we can go back to our axiom, this one. Okay, so this is our first axiom, which imparts the equal sign with its meaning. In ZFC, every term is a set. So x is a set, y is a set. And z is also a set. And sets are filled with sets. So when I earlier said set with 1, 2, 3, 1, 2, and 3 are also sets. We will see later how we can define these, but just know that. So when this says for all, it means just go over every set. Go over every set here and there, and then if for all the other sets that are possible, including themselves, but we will see later that a set can never be an element of itself. For all the sets, if they are an element of the first set, they have to be an element of the second set, and in that case, the two sets are the same. So this also means that if you have a set that is 1 and 3, that is the same as the set with 3 and 1 in it. These two are the same object in terms of set theory. This is the first Zermelo Freankel axiom. The second one, I have to read up on this also because it's been a while. Yeah, the second axiom is a bit boring. I'm not going to explain it. The third axiom is very important to know, and I will write it down in modern notation. This phrasing here has some indefinite amount of quantors in it, which makes it very awkward to write down. It says the following: if you have a set, such as the real numbers, then you can construct a new set using a phrase phi that has some input x, and x is a variable. Phi could be, for instance, x is larger than 0. So this is not a function, this is a phrase. A phrase is a combination of symbols that returns a true value. Sorry, a formula. Phi is a formula. A formula is a set of symbols that can take in some variables and return a true value. So you stitch some symbols together, symbols from the types of symbols that we discussed earlier, and it returns a true value. So phi could be, for instance, x is larger than 0. And then if you have this set, then you can construct a new set, which we call, let's call it R+. And this is the set of, and this is the way that we write that down, is equal to all the x in R for which x larger 0. And the third axiom deals with constructing with the logical rule that is able to construct this set. So you cannot just make any set that you dream of. Every set that you create has to have some axiomatic justifications for its construction. Otherwise, we could say let x be the set containing x, and then we saw that that's already not allowed. So we can't just make every set in set theory. There are some rules about how to construct sets. And the third axiom is the rule that allows you to construct smaller sets from bigger sets using formulas. Again, the phrasing here is awful. Sometimes you see a double dot instead of a line. Some interesting stuff on Wikipedia here. One thing that you can do with the third axiom, let phi be the sentence x is not an element of A, and then A is any set that you can construct, doesn't matter which set you take, and then let this symbol be, I don't know, this is some letter from a Norse language, let this symbol be the set of all the x in the set A for which x is not in A. That means that there's no elements left in this set. So we call this set the empty set, and like you can write it as two squibbles without anything in it. But generally this symbol is accepted to be the symbol for the empty set. And it is the set with no elements. It's one of the most simple sets that you can make. It's also unique. You cannot have a second set with no elements because the set with no elements is always equal to only itself, and you cannot have another set that is not equal to it, which has no elements, by the first axiom. So the fourth axiom defines what it means to take the union of a set. Oh no, this is not a union, but this axiom says that if you have two objects, any objects, so for all x, all y, then you can always construct a set Z for which x is an element in Z and y is an element in Z. Z is just the set containing x and y. So we already saw that we constructed the empty set, so we can also now construct the set that is twice the empty set. But this is actually, this is a rule of set theory. This is the same as just the empty set. So using the third and the first axiom combined with assuming that at least one set exists already gave us two sets, namely the empty set, or three I should say, the random set that we assumed that existed, A, and the set containing the empty set. And now we can use the third axiom again and to say, well, the empty set exists and the set containing it exists. So there must also exist a set with the empty set and the set containing the empty set. You can see how you can sort of build up more complicated structures just by putting shells in shells. And that is sort of how you can create everything using sets. The fifth axiom, this is taking the union. No mathematician learns this by looking at the actual axioms. It's interesting in the context of logic, but I think it's time for us to leave that behind. Except there is one that I want to talk about, and that's the seventh axiom, because this is the one that introduces infinities in mathematics. It's kind of important. Here you can also see what I was just doing. The empty set in a shell, the empty set in a shell with the empty set together in another shell. And you can define the numbers 0, 1, 2, and 3, and 4 in the natural numbers using this. And then the seventh axiom says that there exists some set that doesn't have a largest element. It's just axiomatically defined that that exists, and generally we call that set the natural numbers. So we write that down as a fancy N with a double stripe in it, and that is just the set containing 0, 1, 2, 3, up to infinity, but nothing in between and such. I didn't make that clear in the last videos. Yeah, I'm not going into the phrasing of this. You can look up the Wikipedia article. This is the name of the Wikipedia article that I was reading. So now we've seen set theory, we've seen these Zermelo Freankel axioms. I also said the axiom of choice is also in there, which was a later addition. It's a bit contentious. Some people don't think it is true. It shouldn't be in the theory, but just like constructivists think that our logic is also not true. But every mathematician just uses it, and you're not going to stop them from using it. So it's like arguing against a river that's pulling you down a waterfall. But you can do it if you enjoy that sort of thing. Yeah, so I said we can define the number 1 as, we can define the number 0 as the empty set, and we can define the number 1 as the set containing the empty set. I don't really like these definitions. I think a better definition is we can define a function called the hashtag function. It takes in any set. So its domain is any set, and it maps it to the natural numbers, and it this is, by the way, why some people only use the double arrow. The single arrow is also used for functions that are mapping things to things. So if you want to be unambiguous, the implication arrow should be a double arrow. From context, you should be able to know this means this is a function. What the hashtag function does is it takes a set and it gives you the elements of a set. So if we take our set A from earlier that contained, I don't have it anymore. We had a set A that we defined that contained the number 1, 2, and 3. The hashtag of A is 3. And this is how you can sort of define the numbers, but it's a circular definition, so some people don't like it, whereas this empty set definition is not necessarily circular. We can then define the number 2 as the set with the empty set and the set, and this one like this, which would be equal to 0 and 1 in a set. And then 3 we can define as 0, 1, and 2 in a set, etc., using the third axiom. And then we can use the seventh axiom to put all of these together in a set, and we call that set n. So this is the basics of set theory, and I've gone over Quantors. So to wrap this talk up from what I said earlier about theories that prove statements. So you have a theory which is a bunch of axioms, and it can prove a statement. If you put all the Zermelo Freankel axioms in here, so we have set f1, set f2, etc., and maybe the axiom of choice, then you can use this to prove, for instance, what I said last time. So if you put all the Zermelo Freankel axioms in a big theory, then you can prove the statement in linear algebra that if L is a bijective linear transformation, if and only if its determinant of the matrix representation is 0. For instance, this is just a wacky example, but there's a million examples that you can put here of statements in mathematics that you can prove using the laws of logic that we talked about when we talked about proof trees and such. One more thing about that I forgot to mention about Quantors. I said that there's variables and constants. Variables, when you're writing a formula, and formulas are very important, I kind of neglected to mention them, but I hope you've seen this lecture that they come up all the time. A formula is only complete if all the variables have a quantor assigned. Constants can't have quantors assigned, but variables need to have quantors assigned to them. Quantors are kind of what make variables actually usable. So, for instance, if I write down the formula, and sometimes you've seen me use this double dot is, and this is a shorthand of saying we're not using the actual equation because we're not working within a theory in which equating things is defined, like it is by the first Zermelo Freankel axiom. But we just mean to say when we write this, it's the same as writing the thing on the other side. So phi of x could be a formula like x is 2. But this is not a valid formula because x is a variable and it doesn't have a quantor assigned to it. So I would have to say for all x, x is 2. And if this formula is true, then you would be working in a very boring theory because all your terms are 2. I just want to do some exercises to finish this video off. I will read it out because my handwriting is a bit difficult to read. So this says which of the following formulae are true. The first one has 2 quantors in it, both are natural numbers, and it asks if x is odd, then is x to the power y also odd, and vice versa. Is this true or not? And then the second one, the same but with a square and the real numbers. And then here we have there is an x in R. What do we have again? Oh yeah. So does there exist an Rx so that for every other x, y, this thing hold? And this is multiplication and is smaller than. So next question, write this logically equivalent phrase but without any negations in it. So this has a bunch of negations in it, and I will give you 5 seconds to pause the video and to try this. Grab some pen and paper. 5, 4, 3, 2, 1. Okay, so here are the solutions. This is true, this is false, this is true. And this is the final thing without negations. Let me walk through it, because you know, I like to take some examples. So we saw this in the last lecture, and I stumbled over prime factorization. But the argument with prime factorization holds just as well for any random to the power y, as long as it's a natural number. All of these are natural numbers, so this factorization holds up nicely, since this y times m1 is 0 if it's odd, and y is not 0, m has to be 0, m1. And if m1 is 0, then x is odd. And the exact same argumentation works the other way around. Okay, the second one is false. With a for all statement. So if you want to show that the for all statement is true, you need to show some statement that is general about everything object in the set. But if you want to show that the for all statement is false, you only need one counterexample, and the whole thing collapses. So we take the counterexample of x is being equal to the square root of 2, because the square root of 2 is not divisible by 2, so it's not even though it's a bit weird to ask for a general number if it's even. It only works with natural numbers. So this is a bit of a stupid trick question, of course, but just to show how this works. Truth is dependent on the set you're working in. However, the square is, of course, even, so this doesn't hold. We have an example where the left side is false and the right side is true. Okay, which is in contradiction with this connective. Next sentence. So does there exist an x so that all y, if you multiply them, are smaller than 1? And this is again a bit of a trick question. The answer is, of course, take the number 0 and then you multiply it with y, and yeah, so to show that an existence statement is true, you also only need one example. Whereas with the all statements, to show that it's false, you need one example. So these two are opposites in that way. Okay, so writing this without negations, I put it in 2 parts here. First off, remember that you can flip the negation around. So you flip the Quantors, and then you end up with all is an all, not the thing here. And to negate the relation is larger than or equal to, it's the same as saying is smaller than. So this is again a bit of a trick question. You could have also maybe written a stripe through this if you wanted, but not larger than or equal to is the exact same relation as smaller than. You're not allowed to use the if and only if like this, by the way. It doesn't take in relations as arguments, but you get it. And so then you end up with this sentence. And this sentence is actually really important in the theory of analysis. What this says is, if you read it, by the way, this is another shorthand that you sometimes see used, because we use all epsilon larger than 0 so many times in analysis. Really, this means all epsilon is an element of R, and epsilon is larger than 0. You can also write epsilon is an element of R plus, if you are so inclined. but no one does that. We just write this. So this is the same as saying all epsilon larger than 0. And you can guess this n is a natural number, although in this case it would be true for real numbers, but in general we see this as a natural number. So what does this statement say? It says every positive number you pick, there is always a certain threshold n for which all small n that are larger than this threshold n, 1 divided by this large n, is smaller than your number epsilon. In other words, 1 divided by n gets arbitrarily small. You can make it as small as you want if you make n as big as you need. That's what this statement is saying. So that was Logic 103, and I hope you learned something. I think next time I'm going to go over some more set theory. It's not necessarily logic, but I've used it so much, and it's very important to understanding logic if you've never done any set theory, like most high schoolers haven't, at least in the country that I'm from. Then this is unfollowable, so I will go in a bit more set theory, I think. We already saw the axioms, so you've seen had an introduction of it. See you in the next one. Bye bye.